Next, we can talk about center of gravity. Okay, center of gravity. Actually, the center of gravity of a rigid body is a point where the whole weight of the body is assumed to be concentrated. Okay, supposed to be active, and that point is called the center of gravity. Center of gravity of a body is defined as actually the point where the whole weight of the body is supposed to act. That point is called the center of gravity. Okay, for ordinary bodies, actually the center of mass and center of gravity coincide each other. Okay, for ordinary bodies, actually the center of mass and the center of gravity be coincide with each other. However, for a body such large dimension that G is different at different parts, in that cases, the center of gravity is not coincide with the center of mass. Listen, it in ordinary bodies, actually the center of mass and center of gravity that is coincide, but in the case of such large dimension, the value of G is different for different parts. In that case, in such cases, the center of gravity may not coincide with the center of mass. Suppose when we consider a free space, there G has no sense, but still there actually the center of mass it has some meaning. Okay, in free space, there is no G, so the center of gravity has no sense, but the center of mass has certain definite meaning. Okay, that is about what the center of gravity. Good afternoon, dear children. We can continue the lesson system of particles and rotational motion. Okay, last class we have discussed about the center of mass and also the equation of center of mass. Okay, and also we have derived the equation of motion of center of mass, and also we have learned about law of conservation of linear momentum. Okay, and today's class we can discuss about rigid body. Okay, rigid body, and this in this chapter actually we frequently using the term actually rigid body. Actually, rigid body is one in which the distance between the particles remains unchanged under the application of an external force. Suppose, for example, this is a rigid body, then here one particle is there and here one particle is there, and this much distance between these two particles. And when the application of force or external force, the distance between the particles that remain unchanged, then such a body is called a rigid body. Okay, for example, when we take a stone, actually a rigid body has a different size and shape. Okay, when we consider a stone, even though it does not possess a definite shape, irregular shape, it can be considered as a rigid body. Okay, and here the geometrical shape and the size of a rigid body is unchanged during the motion of the rigid body. Okay, that is during the motion of a rigid body, the geometrical shape and size that also remain unchanged. Okay, actually rigid body consists of what an assembly of point objects. Okay, a rigid body actually consists of an assembly of point objects, and the mutual distance between them, or the mutual distance between different point objects that remain unchanged during the motion of the rigid body. That is actually the peculiarity of the rigid body. Okay, that is the rigid body can be considered as the collection of several point objects, and during the motion of a rigid body, the distance between the point objects that remain unchanged. Okay, actually the concept of rigid body is an idealized concept. Okay, and but this concept is of great use actually in the study of rotational motion of the rigid body. Okay, the concept of rigid body is an idealized concept, but this concept is of great use in the rotational motion of rigid body. No, actually, no ideal, no real body or body are truly what rigid. Okay, no real body are truly actually rigid. Okay, the next we can talk about the center of mass of a rigid body. Okay, center of mass of a rigid body. Center of mass actually we have already learned. Here the center of mass of a rigid body means whose position is fixed. Okay, whose position is actually it is a point on the rigid body. Okay, the center of mass of a rigid body is a point whose position is fixed with respect to the body as a whole, isn't it? The center of mass of a rigid body is a point whose position is fixed with respect to the body as a whole. Okay, actually this point may be may or may not be within the body. Okay, actually the center of mass, it may or may not be within the body. Actually the center of mass of a rigid body, that depends upon the shape of the body and distribution of mass in the body. Okay, then what are the factors on which the center of mass of a rigid body that depends? First is the shape of the body and the distribution of mass of the body. Distribution of mass in the body. Okay, the shape of the body and the distribution of mass in the body. Actually, in the case of symmetrical bodies, the center of mass is exactly at the lies at the center. In the case of symmetrical objects, the center of mass lies exactly at the center. Okay, then we can talk about certain symmetrical bodies and the position of center of mass. Next, we can talk about some symmetrical bodies and the position of center of mass. When we consider a uniform rod, the center of mass that lies at the center. Okay, for a uniform rod, the center of mass lies at the center. Then the square or rectangle, actually the center of mass lies in the position of point of intersection of diagonals. Okay, in the case of a square or rectangle, the center of mass lies at the point of intersection of the diagonals. In the case of uniform circular ring, actually the center of mass lies at the center of ring. In the case of uniform circular disc, the center of mass is at the center of disc. In the case of a uniform solid sphere and in the case of uniform hollow sphere, the center of mass lies at the center. Okay, in the case of uniform solid sphere, the center of mass lies at the center of solid sphere, and in the case of uniform hollow sphere, the center of mass lies at the center of hollow sphere. Okay, and in the case of cubical block, the position of center of mass is at the point of intersection of diagonals. Okay, in the case of cubical block, the center of mass lies at the point of intersection of diagonals. Okay, that is about some symmetrical bodies and the position of center of mass. Okay, suppose if a rigid body has an irregular and irregular shape and the distribution of mass is not uniform, it is very difficult to locate the position of center of mass. We already said the center of mass actually depends upon the center of mass of a rigid body actually depends upon the shape of the body and the distribution of mass in the body. And suppose if the object has an irregular shape and the distribution of mass is not uniform, it is very difficult to find out the center of mass. And in such complicated cases, we either employ the techniques of integral calculus or by the use of geometrical consideration, we can locate the position of what center of mass. Okay, in the suppose if the rigid body has an irregular shape and the distribution of mass is not uniform, it is difficult to locate the position of center of mass. And in such cases, we employ the techniques of integral calculus or by considering geometry, we can locate the position of center of mass. Okay, all of you got it? Next, we can talk about center of gravity. Okay, center of gravity. Actually, the center of gravity of a rigid body is a point where the whole weight of the body is assumed to be concentrated. Okay, supposed to be active, and that point is called the center of gravity. Center of gravity of a body is defined as actually the point where the whole weight of the body is supposed to act. That point is called the center of gravity. Okay, for ordinary bodies, actually the center of mass and center of gravity coincide each other. Okay, for ordinary bodies, actually the center of mass and the center of gravity we coincide with each other. However, for a body such large dimension that G is different at different parts, in that cases, the center of gravity is not coincide with the center of mass. Listen, it in ordinary bodies, actually the center of mass and center of gravity that is coincide, but in the case of such large dimension, the value of g is different for different parts. In that case, in such cases, the center of gravity may not coincide with the center of mass. Suppose when we consider a free space, there g has no sense, but still there actually the center of mass, it has some meaning. Okay, in free space, there is no g, so the center of gravity has no sense, but the center of mass has certain definite meaning. Okay, that is about what the center of gravity. Next, about torque or moment of force. Torque or moment of force. Okay, actually, here we are considering a body which is free to rotate about an axis O. Okay, here we are considering a body which is free to rotate about an axis O, passing axis through O. Okay, and here a horizontal force is applied. A horizontal force is applied on it at a point P. Okay, here a horizontal force is applied at the point P. Rotate it about its axis. Okay, and if d is the perpendicular distance between the axis of rotation and the line of action of force, actually this is the line of action of force. Here the d that represents the perpendicular distance between the axis of rotation and the line of action of force, isn't it? If d is the perpendicular distance of the line of action of force from the axis of rotation, then the torque or moment of force about the axis of rotation is torque. Actually, it is represented as tau. Okay, torque tau is equal to force into that perpendicular distance. That is F into, here the perpendicular distance is d. Okay, F into d. This is actually torque. Okay, torque can be measured as the force into the perpendicular distance between the axis of rotation and the line of action of forces. So torque tau can be written as F into d. Actually, the torque or moment of force is the turning effect of the force about its axis of rotation. Okay, torque or moment of force is the turning effect of force about the axis of rotation. Okay, actually it is measured as the product of magnitude of force. How we can measure torque? Torque can be measured as the product of magnitude of force into perpendicular distance between the axis of rotation and the line of action of force. Okay, this is actually torque. Torque or moment of force is the turning effect of force about the axis of rotation, and it can be measured as the product of magnitude of force and the perpendicular distance between the axis of rotation and the line of action of force. Okay, torque can be represented as tau, that is equal to force into distance. So we can write torque tau is equal to F into d, force into distance. Okay, actually it is measured as the product of magnitude of force and the perpendicular distance between the axis of rotation and the line of action of force. Okay, that is about torque and moment of force. Next we can talk about couple and moment of couple. Okay, here for example we are considering two opposite forces, each of magnitude F. These two are opposite forces, each of magnitude F. They acts at two different points A and B. Okay, these two forces acts at two different points A and B of a rigid body, and which can rotate about the point O. This rigid body can rotate about the point O. Actually, the turning effect of this force is along the anti-clockwise direction. The turning effect of these forces is actually along the anti-clockwise. Okay, and here a pair of equal and opposite forces acts at two different lines of action. Okay, along two different lines of action that constitute a couple. That is actually called what? Couple. Okay, a pair of equal and opposite forces acting on a body along two different line of action constitute a couple. Okay, what is meant by actually couple? A pair of a pair of equal and opposite forces acting on a body along two different line of action. These two forces acts along two different line of action that constitute a couple. So for example, actually when we steer a bicycle around a bend with our both hands on the handlebars, we apply a couple. Okay, when we steer a bicycle around a bend with our both hands on the handlebars, we apply a couple. Okay, that is actually couple. Then how we can calculate the moment of couple? Okay, we can calculate what the moment of couple. Actually, moment of couple is actually torque itself. The moment of force or moment of couple is actually torque itself. Okay, so the moment of couple is actually is equal to torque tau. Okay, that is equal to, either the force, here we have two forces. So either the force into the perpendicular distance between these two forces. One force is along this and another force is along this. Actually, this is the perpendicular distance between the two forces. So we can write tau is equal to F into the perpendicular distance is AB, which is actually F into D. Okay, F into D. So the moment of couple can be measured as the product of either the force, magnitude of either the force and the perpendicular distance between the two forces. Okay, moment of couple can be measured as the product of either the force and the perpendicular distance between the two forces. Actually, moment of couple is actually torque itself. That is also called the moment of force, isn't it? And here we can write the vector representation of torque as, torque tau is equal to r cross f. The distance d can be taken as r. Okay, we can take instead of d here r as the the perpendicular distance between the two forces. So we can write tau is equal to r cross f. What is a cross b? How we can write a cross b? I think already we learned a cross b equal to ab sin theta. Similarly, r cross f can be written as what? R of sin theta. R cross f is what? R of sin theta. Okay, actually this is the vector notation of torque tau. Okay, torque. Okay, torque tau can be written as equal to the vector representation. Torque is equal to r cross f, which can be written, we can expand this r cross f as rf sin theta. So torque tau is equal to rf sin theta. Very, very important relation. Torque tau is equal to r cross f, which is equal to r of sin theta. R cross f, which is equal to r of sin theta. Okay, that is actually about couple and moment of couple. Actually, a pair of equal and opposite forces acting on a body along two different lines of action that constitute a couple. Okay, actually here due to this couple the turning effect is produced. Okay, so we can calculate the moment of couple or torque acting on this rigid body, that is represented as torque tau, that is equal to force. Either the force, we can measure the moment of force as the product of either the force and perpendicular distance between the two forces. So torque tau is equal to F into AB, which can be written as F into D. Then how we can represent the torque in vector representation? Okay, that is torque is equal to R cross F. Torque is equal to R cross F, which can be written as R of sin theta. Torque tau is equal to what? R of sin theta. Next we can talk about angular momentum. Angular momentum, actually this is represented by L. Okay, all of you know in translational motion we have already learned about linear momentum. That is represented by P. Linear momentum is the product of mass and velocity. That is already we learned in translational motion. Actually, angular momentum is the rotational analog of what? Linear momentum. Okay, in rotational motion, instead of linear momentum, we have to learn about what? Angular momentum. Actually, it is the rotational analog of linear momentum. Okay, actually in translational motion we have learned about force. Actually, its rotational analog is actually torque. Okay, in rotational motion, instead of force, we have to mention the force as, we name that force as torque. Actually, torque is the rotational analog of what? Force. Okay. And here in translation motion, we have learned about linear momentum. But in rotational motion, we have to learn about angular momentum, which is the rotational analog of linear momentum. Okay, which is the rotational analog of what? Linear momentum. Okay, then what is angular momentum means what? Actually, it is concerned with the rotating particle. Okay, rotating body. So the angular momentum of a rotating particle about an axis of rotation is the moment of linear momentum. What is it? Moment of linear momentum. Okay, moment of linear momentum of a particle about that axis. Okay, moment of linear momentum means linear momentum into distance. Momentum means actually concerned with the distance. Okay, moment of force means force into distance. Okay, moment of couple we have already learned, or moment of force. Force into distance, that thing actually gives torque. Okay, moment of force. Moment of force means force into distance. This moment means actually concerned with the distance. So moment of force means force into distance. That actually gives torque. Here the moment of linear momentum is linear momentum into what? Distance. Linear momentum into distance. That thing actually gives angular momentum. Linear momentum into distance, that will gives what? Angular momentum. Okay, so angular momentum of a rotating particle about an axis of rotation, rotation is the moment of, is what? A moment of linear momentum of the particle about that axis. Okay, angular momentum of a rotating particle about an axis of rotation is the moment of linear momentum of that particle about that axis. Okay, actually how we can measure this angular momentum? Actually this can be measured as the product of linear momentum. Okay, angular momentum can be measured as the product of linear momentum and the perpendicular distance of that particle from the axis of rotation. Okay, angular momentum can be measured as the product of linear momentum and the perpendicular distance of that particle from the axis of rotation. Okay, so angular momentum L can be written as R into P. So we can write R cross P. Angular momentum L is equal to R cross P. Okay, this is the vector representation of angular momentum. L is equal to R cross P, which can be written as what? A cross B can be written as AB sin theta. Similarly, R cross P can be written as RP sin theta. R cross P can be written as RP sin theta. But you know what is momentum P, linear momentum? You know the equation, mass into velocity, momentum. So we can write instead of P, we can write MV sin theta. We can write MVR sin theta. This is the expression for angular momentum L. MVR sin theta. MVR sin theta. That is the expression for what? Angular momentum. Okay, actually angular momentum is the rotational analog of what? Linear momentum. Actually angular momentum of a particle, rotating particle about an axis of rotation is the moment of linear momentum of that particle about that axis. Okay. Angular momentum of a rotating particle about an axis of rotation is the moment of linear momentum of the particle about that axis. Then how we can measure angular momentum? It can be measured as the product of linear momentum of the particle and the perpendicular distance of that particle from the axis of rotation. So we can write angular momentum L is equal to R cross P, which can be written as RP sin theta. Then substituting P as M into V. So rearranging this, the angular momentum L can be written as MVR sin theta. This is also very important relation. Angular momentum L equal to R cross P. Angular momentum L equal to R cross P, which is equal to RP sin theta. Okay, that is about angular momentum. Next, we can establish a relation between torque and angular momentum. So, relation between torque and angular momentum. Okay, you can establish a relation between torque and angular momentum. Okay, all of you know the angular momentum L can be written as R cross P. Okay, angular momentum L is equal to R cross P. Next, we can differentiate this equation with respect to time. Okay, we can differentiate this equation with respect to time. That is dl by dt. Okay, dl by dt is equal to, this thing we already, here we have to apply the product rule in differentiation. That thing we have already learned, the product rule. That is d by dt of u into v. How we can, this is the standard equation, d by dt of uv. What is, how we can write it? First derivative of first du by dt into v plus what, v into, sorry, u into dv by dt. That is the standard equation. Okay, that is the derivative of first into second function. Here we have two functions u and v. Derivative of first into second function plus first function into derivative of second. That is du by dt into v plus u into dv by dt. Similarly, we can differentiate R cross P. How we can differentiate R cross P? Differential of first, that is dr by dt cross P plus first function into R into derivative of second, that is d cross dp by dt. This is actually the differential of R cross P. dr by dt cross P plus R cross dp by dt. Isn't it? Next we can write dr by dt. All of you know what is rate of change of displacement, dr by dt. That is velocity v. So v cross, instead of momentum p, we can write m into v. Okay, plus r cross by Newton's second law, you know dp by dt. What is dp by dt? Rate of change of momentum. That is equal to the force. That is by Newton's second law. The rate of change of momentum is equal to force. So it is r cross f. Okay, and this m can be written first. That is m into v cross v plus what is r cross f? You know what is r cross f? What is r cross f actually? Torque tau. Okay. Then what about v cross v? That is the cross product of the same quantity itself. Across a, we already learned in vectors. Okay, v cross v is actually 0. So we got dl by dt is equal to torque tau. That is the relation between torque and angular momentum. dl by dt is equal to torque. Okay, that is the torque is the rate of change of angular momentum. The rate of change of angular momentum is actually torque. But in translation motion, we have already learned the rate of change of momentum, that is linear momentum, is force. But in that is in translational motion, the rate of change of momentum or the linear momentum is force. And here in rotational motion, the rate of change of angular momentum is equal to the torque. That is the relation between angular momentum and torque. This is also very important. Okay, the rate of change of angular momentum is equal to the torque. Okay, I am repeating here. The angular momentum, that thing you know, the angular momentum L can be written as R cross P. Angular momentum L is equal to R cross P. Then we can differentiate it with respect to time. So dl by dt is equal to d by dt of R cross P. Okay, d by dt of R cross B. Here we have to apply the product rule. Because we have two functions, so we have to apply product rule. So we have the standard equation d by dt of uv, that is equal to du by dt, that is derivative of first into second function plus first function into derivative of second, that is u into dv by dt. That thing we can apply here. Derivative of first, that is dr by dt into second function p plus first function r into derivative of second function, that is dp by dt. Okay, but you know dr by dt, rate of change of displacement, that is actually velocity v. So v cross p can be written as what is p? Momentum is a product of mass and velocity. So we can write m into v plus r into here dp by dt. You know what is dp by dt? Rate of change of momentum. By Newton's second law, dp by dt is equal to the force. So instead of dp by dt, we can write F. Then m can be written first. So m into v cross v plus, you know what is r cross f? R cross f is actually torque. So we can write torque. And here v cross v, that is the cross product of the same quantity with itself, that is actually 0. Okay, so v cross v can be written as 0. So we got dl by dt is equal to torque tau. That is the relation between angular momentum and torque. That is the rate of change of angular momentum is equal to the torque. Okay, the rate of change of angular momentum is equal to the torque. That is the relation between torque and angular momentum. Next, we can talk about law of conservation of angular momentum. Law of conservation of angular momentum. Okay, all of you know the relation between torque and angular momentum. What is the relation between torque and angular momentum? dl by dt is equal to, you know, torque tau. dl by dt is equal to tau. Suppose if tau is equal to 0, that is torque is equal to 0, then what is dl by dt? dl by dt is equal to 0. All of you know the derivative of a constant is 0. That is the rule. The derivative of constant is 0. If dl by dt is equal to 0, that means L is a constant. L is a constant. Okay, that is, if no external torque acting on a particle, its angular momentum remains a constant. If no external torque acting on a particle, its angular momentum remains a constant. Okay. In translation motion, actually we have learned about law of conservation of linear momentum. That thing we already learned. Law of conservation of linear momentum. That is, if no external force acting on a system of particles, its total linear momentum remains a constant. This actually this is the rotational analog of that thing. Law of conservation of linear momentum. Okay. So here we have to, in rotational motion, here we have the law of conservation of angular momentum. Okay, in rotational motion, instead of linear momentum, we have to talk about angular momentum. Okay, so here we have a law of conservation of angular momentum. Okay, for that we are considering the relation dl by dt is equal to torque tau. dl by dt is equal to tau. If tau is equal to 0, then what about dl by dt? That is 0. Okay, all of you know the derivative of a constant is 0. Here the derivative of L is 0. So L must be a constant. L is a constant. So according to law of conservation of angular momentum, if no external torque acting on a particle, its angular momentum remains a constant. Okay, according to law of conservation of angular momentum, if no external torque acting on a particle, its total angular momentum remains a constant. Okay, all of you got it? That is about law of conservation of angular momentum. Okay, children, today's class we have learned about the rigid body. Okay, and about center of mass. Then actually it is a point where or the whole mass of the body is assumed to be concentrated. When we have learned about center of gravity, where it is a point where the whole weight is assumed to be acting, that is center of gravity. Okay, next we have learned about what moment of couple or moment of force. Actually it is equal to the torque itself. That is it is the product of either the force and perpendicular distance between the two forces. Okay, next we have learned about angular momentum. Okay, the next the relation between angular momentum and torque, that is dl by dt is equal to torque tau. Next about the law of conservation of angular momentum. Okay, children, that is the end of today's class. Thank you.